This is the ME4056 PID Control Lab. Sarah Violante, Tibor Gyorfi,
Yujung Ryu.
There are three main objectives in this lab. The first objective is to introduce the effects of control gains, Kp, Kd, and Ki, on restoring a system to a desired value. The second objective compares experimental models with theoretical models generated in Simulink and observes the differences between P, PD, and PID control. And the last objective tunes the motor to determine the appropriate gains that will provide the client's specifications. The apparatus is shown below. There are three procedures conducted in this lab. The first part, the motor board is hooked up to the MyRio. The MyRio sends signals to the command and received by the encoder. Each type of controller gain is isolated to determine the effect on restorative torque when rotating the flywheel by hand. In the second part, a square pulse wave is generated from the VI. Responses of P, PD, and PID control were collected using the motor gain obtained from the previous lab. The procedure is repeated with the sawtooth signal. Lastly, starting with only P and working up to PID, the control gains are varied until the response meets the specifications. The same experimental setup is shown below. So here we have our KD, KP, and KI control plots, and we have qualitative observations for these. For proportional control, the restoring torque relied on the error itself. For derivative control, it relied on the speed at which the error changed. For integral control, the restoring torque depends on the integral of the error over time, otherwise known as the sum, which explains why the system overreacted itself and the error went out of control. There is a spring mass damper analogy here. Since a spring constant is a proportion of a spring's force to its displacement, the Kp gain most resembles a spring. Additionally, the way a Kd control depends on the change in error over time likens it most to a damper because a damping constant is attached to velocity. Integral is unstable because the sum of the error is a poor representative of the error itself. Because the restorative torque is using the sum of the error over time, this becomes infinitely large and the restorative torque overcorrects itself. Adding mass to the flywheel, lastly, increases the time constant, however, the overall trend remains the same.
The controller gain is determined based on the motor constant and time constant that was calculated from the previous lab, and also based on the controller specification that was given. The table 1 shows the gain value that was used for this lab. Table 2 shows the square pulse tracking results. Based on the score on the graph, PD controller performed the best and the PID controller performed the worst. Since the score is based on the percent overshoot and the steady state time, this is expected to some degree, because increased integration value results in the overshoot while not helping much with the settling time. This result is expected. But we need integration in order to account for the steady state error. Figure 6, 7, and 8 shows P, PD, and PID controller for the square wave. The experimental model for all of them takes longer to reach the input value. Also, it takes longer to reach the steady state as a result. This is expected because the inductance and friction within the system is not accounted for the theoretical model. Also, the motor with the weight is not totally balanced, which may also affect the result. Issue with the P and PD controller is that it does not take the integration into account, therefore may never reach the steady state value. However, when the value of integration is too high, it may result in huge overshoot.
The same trend is observed in the sawtooth pulse, as shown in the data below. It is also seen in the P, PD, and PID plots.
Figure 12 and 13 each shows the optimization trials for square and sawtooth wave. Table 4 shows the effect of each gain increase on overshoot settling time and steady state error. However, the D gain increased with respect to the settling time somehow did not follow the theoretical trend of decrease. PID controller with the square input is better for satisfying the client's specifications. First, the square wave is better than the sawtooth that one can track all the variables. Second, the PID controllers gives the 3 variables that can be modified to get the specification for each variable. Optimized PID values from the square wave does result in favorable tracking for the sawtooth wave too, as shown in trial 4 for the sawtooth. However, for the sawtooth signal, maximum overshoot and the settling time cannot be calculated. In conclusion, PID control is a better way to control the signal because it is easier to achieve the specification that may be given by the client. The experimental system may not always follow the theoretical system due to many other factors, such as friction, unbalanced flywheels. Knowing the effect of each gain helps to manipulate the system in order to achieve the target for overshoot, settling time, and steady state.